Hello, you're welcome back. All right, so we are looking at work, energy, and power, three in one topic. So I'm gonna start with work. All right. So what is work? How do we define work in physics? Now, work in physics is defined as the product of force, and distance. Okay, in the direction of the force. The product of force applied and the distance moved in that direction of the force. All right. For example, let's say you got a load and you needed to move this load to a distance. A distance. Let me just use D. A distance D. Okay. Then you needed by the application of a force F. So the work that is done here is gonna be equal to force times distance. So which simply means that work is actually work is a vector quantity. And we know that the SI unit of work is actually joule. Okay, it's a scalar quantity. Please pardon me. Work is a scalar quantity. Why? Because okay, there is no both the distance and the force applied must be in the same is in the same direction. Okay, there is no disparity. Um, between the force applied, the direction of the force applied, and the distance. Okay, so the distance moved by the body and the force applied is in the same direction. Now, what happens when the force applied, okay, the force applied to that body is inclined at an angle? How do you calculate the work? For example, let's look at a situation where you have this body, okay, and a force is the force F applied to this body happen to incline at an angle with the horizontal. Okay, let's say the force is inclined at an angle theta. Okay, and let's this I will still need to move this the body to a distance d. How then can you calculate the work, knowing quite well that the force and the distance must be in the same direction? So for me to evaluate this work, I will have to resolve the force, okay, to the horizontal dimension. And of course, when we treated vectors, I taught you how to resolve a vector quantity, okay, in the horizontal dimension. So I'm going to find the horizontal component of the force F. So in this case now, if I'm being asked to evaluate the work, okay, so the work done is going to be equal to um, the horizontal component of the force, which of course is F cos theta. Horizontal component of the force is F cos theta, then multiply by the distance d. Okay, so I hope that is well understood. All right, so that is how we we evaluate work. So for example, let's say a force of 20 newton was applied to this body, and this force was applied at an angle of 60 degrees 60 degrees to the horizontal to move this body a distance of 2 meters. Okay, so if you are to evaluate the work, simple, that's going to be the force is 20 newton 20. Okay, 20, then multiply by cos of the angle cos 60, then times the distance, which of course is 2, times the distance 2. So it's going to be equal to 20 cos 60 is 0.5, then multiply by 2. So 0.5 times 20, that's going to be 10. 10 times 2, that's 20 joule. Okay, so the work here is 20 joule. All right, now let's actually now discuss energy. Okay, what is energy? Now, energy is actually defined as the ability. Okay, energy is the ability to do work. So that is why energy and work share the same SI unit. So they are actually the same. Okay, I can simply say that energy is equal to work. Energy is equal to work. The only difference is this. Okay, before work can be done, energy must be stored. Okay, so energy is stored while work is actually being done. So invariably, work is actually uh, done when there is energy. Without energy, there is no work. All right. Okay. Let's take for example, a battery stores chemical energy. A battery stores chemical energy. Okay. So with this chemical energy, if you connect a bulb across the battery, okay, that chemical energy that is stored will now actually do work by moving electron across the conductor to light your bulb. So work and energy, they are the same. The only difference is that energy is being stored, and that energy that is stored, okay, when it is being expended, it will now lead to the uh, doing of work. So that is why both work and energy, okay, share the same SI unit, which of course is joule. So now here we're going to be looking at the different forms of energy, okay, different forms of energy. Now, energy is of these different forms. All right. Number one, we have mechanical energy. Of course, a system that is on motion possesses mechanical energy, or a system that has the tendency to move, that have the properties of movement, possesses mechanical energy. We have also electrical energy. These are different forms of energy. We have light energy, energy from a lightning system. We have um, heat energy. Okay, we have heat energy. We have chemical energy, of course, stored in a chemical system. Even sound is an energy. Sound is an energy. Nuclear energy, etc. Okay, these are different forms of energy. All right, so now we're going to be looking at what is known as the law of conservation of energy. Okay, so such law actually states that energy can neither be created. Okay, you can't create energy. Energy can neither be created nor can it be destroyed. So, but it can be transformed from one particular state to another. So, which simply means that any of this energy that you have at a particular point being expressed, okay, or being seen as, let's say, in form of a work, all right, it is actually gotten from another energy. So it wasn't created. It was another energy. It's another form of energy that actually transformed to what you have. For example, let's take a typical example. Okay, chemical energy that is, of course, that is stored by a battery. So when you connect a wire across that battery, that's chemical energy. Of course, you connect wire across the battery, then you connect the wire across a bulb. All right. So that chemical energy will be transformed into um, chemical energy will be transformed into electrical energy. From the electrical energy now, it will now light your bulb into light energy. Right. So energy can neither be created nor be destroyed, but it can be converted from one form to another. All right. So Just once you just see a system that is operational, you can actually know the energy conversion that actually leads to the operation of that system. Okay, I can also give you another example. Let's look at mechanical energy of a generator. Okay, AC generator. AC generator actually rotates. As it rotates, it generates electrical energy, and that electrical energy can be used either as light, converted to light, or it can be converted to heat. Okay, for um, uh, a pressing iron, right? So that is this. Now, among all this energy, we're going to discuss the very first, which is mechanical energy. Okay, we discuss mechanical energy. Mechanical energy. All right. Now, mechanical energy, okay, is of course the energy of a system that is undergoing motion. Okay, so any system that is undergoing motion produces mechanical energy. So before that system actually undergoes motion, okay, there are two things are involved. That system must actually be displaced. It will be displaced first before it can now, that displacement is translated into motion. That is why we actually divide, or mechanical energy is actually divided into two types. Okay, so mechanical energies of two types, which include potential energy. Then the second, we have the kinetic energy. All right. Okay. Now let's start with potential energy. All right. The idea, which of course I'll call it, is a primary, definition of the potential energy. Where, okay, you are meant to understand that potential energy is energy of a body at rest. Okay. As you actually go advance in sciences, you discover that that is wrong. Not all the body that is at rest, okay, possess potential energy. Rather, potential energy of a body is the energy due to the position of that body. So, position of the body or even the displacement. Okay. So, if that body is actually positioned at a particular height or it is actually displaced, why? Because every potential energy, once released, must always be converted to kinetic energy. So the kinetic energy that you see of a body that is moving, a body will start motion only if, okay, if that body starts a motion, if it's actually displaced or placed at a position in which, if it is being released, okay, then it will start motion. Okay, let's say for example, if you actually raise a ball to a particular height and release it, it will not remain at that height. Okay, it will just fall down due to the influence of gravity. That is one example. Another example, okay, of potential energy is, let's look at catapult. A catapult that is actually being stretched. Now, as you stretch that catapult, you have actually displaced it. Okay, you have extended it. As you stretch it, it actually stores potential energy. And once it's being released, the stone inside of it will gain energy, which of course is actually converted to kinetic energy. Okay, so that is why potential energy is energy as a result of position of that particular object or its displacement. So now the formula for potential energy, let me just use P. Okay, so potential energy is given as mgh. This potential energy due to a body that is raised at a height and released to fall against gravity. Of course, you know what the H represents. Okay, the H is the height. The height where that particular body was projected. The M is the mass of the body. Okay, of course, the G is acceleration due to gravity. So please take note of that. Now, what of kinetic energy? So, as I already said, a body possesses potential energy. Once it is being released, its energy is now converted into kinetic energy. So, the energy of a body that is already in motion, okay, that is in motion, the energy possessed by a body in motion is potential, is kinetic energy, please pardon me, kinetic energy. So, now kinetic energy by formula is equal to half mv square. Of course, we know that m still remain the mass of the body. Then the v is now going to be equal to is the velocity of that particular object. Okay, so I hope that is well understood. All right, so now we are going to be looking at the law of conservation. Law of conservation. Of mechanical energy, ME. Okay, so uh, as we've already stated the law of conservation of energy, so the law of conservation of mechanical energy actually states that mechanical energy can never be created nor destroyed. Okay, but mechanical energy, okay, is actually transformed from potential energy to kinetic energy, and of course vice versa from kinetic energy. So the conversion between potential energy to kinetic energy, or even the conversion that actually leads to both potential energy and kinetic energy. So this interconversion between potential energy and kinetic energy is what actually give rise to mechanical energy. Okay, so it is not created, it is the interconversion between potential energy and kinetic energy that actually give rise to uh, mechanical energy. So which simply means that anytime you have a kinetic energy, that kinetic energy, okay, if it was the only thing the system actually exhibit at that particular point, doesn't just come, okay, it wasn't created, it came from the original potential energy. Remember what I told you about a catapult, okay, that is actually being displaced. That catapult is being displaced at that point, it doesn't have any kinetic energy. The kinetic energy at that point is zero, but the potential energy is maximum. But as it was released, that potential energy was automatically converted, so to automatically convert it to a kinetic energy. Another example is when a ball is being projected at a height, okay, and that ball is released. When this ball is being released to fall at this height of projection, remember that the ball is not moving. So what it has at that point is maximum potential energy. Meanwhile, the kinetic energy at that particular point is equal to zero. So when the ball is being released now, this potential energy now, okay, is what leads to let's say the ball is being released, then the ball is now moving at this height. Okay, it's at this height. At this point now, the ball possesses both potential energy plus kinetic energy. Okay, why? Because the ball is on motion, and of course, it still possesses height. Okay, it still possesses height. So this potential energy that is actually that you get here wasn't created from anywhere, but rather it was the initial potential energy that was converted. Okay, so let's even look at the same what happened when the ball now want to hit at the point where that ball want to hit the ground. At that point where the ball want to hit the ground, where there is no height again, okay, what you have at that very moment, what you have at that instance is um, purely kinetic energy. Kinetic energy at this point now is maximum. And now there's no more potential energy. Potential energy is 4 to 0. So this maximum kinetic energy, was it created? No, it wasn't created. It still came from everything come from the initial potential energy. So that is why I said that for law of conservation of mechanical energy, okay, to be observed, the kinetic energy you get, let's say as the motion, okay, as that body is now in motion, of a body that is in motion was, okay, actually came from the original potential energy. So sometimes you see a question where you be asked to calculate, can you be asked to calculate kinetic energy. You may not need to, okay, use the formula of kinetic energy, which is half mv squared. At that particular instance, what you're gonna be evaluating is potential energy, because it was this potential energy that was converted to kinetic energy. Okay, so let's look at a typical example. Okay, let's look at a question where in which, okay, you are told that a ball of 2 kg was projected at a height of 10 meter. Okay, now the question is, if it is being released, okay, probably with a velocity of 2 meter per second, what is the kinetic energy just before it hits the ground? So we are looking for the kinetic energy just before, okay, it hits the ground. Before it hits the ground, the height at that particular, the height is 0, okay? So the kinetic energy, and of course, from what we have already learned, according to the law of conservation of kinetic energy, the kinetic energy just before that object hits the ground is equal to the initial potential energy of that particular body, okay? And the initial potential energy is given as mgh. The mass of the body is 2 kg. G, of course, acceleration due to gravity is 10. Then the height is actually 10. So 2 times 10 is 20. 20 times 10, that's going to give me, that's going to give 2,000. That's 2,000 joules. All right. So just take note of this principle, the law. We'll definitely apply them. Okay. We're going to apply all this formula in the next video. But let's now discuss power, which of course is the last part of this, the last topic in this series. Okay. Now, power. What is power? All right. Now, power is defined as, please pardon me. Power is defined as the rate at which work is done. So, of course, rate is always with respect to time. So, power is defined as the rate at which work is done. That simply means that power is equal to the work done divided by the time, okay, for the work to be done. And the SI unit of power is watt. Okay, since we know that work is also equal to energy, we can also express power to be equal to the energy. Okay, energy, then of course divided by time. Energy all over time. Apart from this, there's another way of I can also express power. All right, power. There's another formula for power. We already know that work is force times distance, then of course divided by time. Okay, so now in motion, we know that distance all over time, distance moved, okay, by an object divided by time is velocity. So power can also be expressed as force times the speed or velocity. Of course, speed and velocity, they are the same. It's just that one has direction while the other one doesn't. But in this case, okay, since I'm dealing with a scalar quantity, so speed and velocity would mean the same thing. All right. So I'm gonna have power is equal to force times velocity. So it's either you evaluate power to be equal to work all over time, energy all over time, or you evaluate work to be equal to, okay, force multiplied by the velocity. Now let's look at a typical example. Okay, let's look at a situation where a mass of 10 kg was lifted to a height of 10 meter, and that happened within 10 seconds. Okay, so the question is, what is the power that is expended by actually doing this work, lifting this object to a height of 10 meter? Okay, so in this case, we're going to use energy, which of course is the potential energy divided by the time. So the potential energy is going to be 10 times 10. That's acceleration due to gravity times the height, which of course is 10 meter, divided by the time. Okay, of course, the 10 seconds represent time divided by the time. So of course, by dividing, I will have that the power, okay, that is actually expended by doing this work is 100 watt. So we are going to be looking at more questions in the next video. All right. See you in the next video. Thank you very much.